Welcome to Efiwe, excellence without stress.
Welcome guys to Efiwe, excellence without stress. Now, have you guys ever wondered why taking too much vitamin C tablets at the same time causes blisters on the palate of your mouth? Or why it just makes sense not to use a metallic container to carry an acid? Or what is responsible for the sour taste of some fruits? Or even some spoiled food? This will be understood as we go through the journey of learning acid, bases, and salts. The content is going to be divided into these sections or these subparts. Let's get into the study. The first person that postulated the definition of an acid is Arrhenius. And according to him, an acid is defined as any substance that dissolves in water to produce hydrogen ion as the only positive ion. Examples of such acids include sulfuric acid, hydrochloric acid, and your nitric acid. But let's get to understand exactly what he means by looking at the screen. So, we're going to be considering two substances just to explain my definition. If you have sodium chloride, for instance, and you want to dissolve sodium chloride in water, the first thing you need to take note of is that water undergoes a partial dissociation to produce hydrogen ion and hydroxyl ion. Now, on introducing sodium chloride into this particular water, you will notice that sodium chloride, according to ionic theory, should split to form ions, and it's going to form sodium ion and chlorine ion. According to Arrhenius, when a substance dissolves in water and you notice that the only positive ions becomes hydrogen or are hydrogen, the implication is that that substance is an acid. If you look at this now, notice that NaCl was dissolved in water, but then the positive ions include sodium and hydrogen ion, which means obviously and most definitely this is not an acid. Now, but if you happen to dissolve something like HCl in water, as I stated earlier, that water undergoes a partial dissociation to give hydrogen ion and hydroxyl ion. On dissolving HCl in water, you are going to get H plus Cl minus. Consider the only positive ions here and notice that they are all hydrogen. The implication is that obviously this is an acid. So just have that in mind, that when you are considering or trying to understand or identify an acid, according to Arrhenius, it is simply any substance that dissolves in water to produce hydrogen ion as the only positive ion. Okay, what then does he describe a base as? An Arrhenius base is described as any substance that produces a hydroxide ion when dissolved in water. Also, a base is simply defined as any substance that will neutralize an acid to yield a salt and water as the only product of the reaction. Things to take note of is the fact that most oxides and hydroxides of metals are bases. It doesn't mean that every base is a oxide or hydroxide of a metal. But the point is this, that once you are considering a hydroxide or an oxide of a metal, most of them are bases. Examples: your sodium oxide, potassium oxide, sodium hydroxide, magnesium oxide, potassium hydroxide, and the rest of them. Now, with that said, an alkali is then defined as a basic hydroxide which is soluble in water. And your most important examples of alkalis include sodium hydroxide, potassium hydroxide, and calcium hydroxide. With this said, when you are referring to alkalis, it is not generally describing every base, but describing soluble base. So the implication is that every alkalis is a base, but not all bases are alkalis. Moving ahead. A basic oxide is a metallic oxide which contains ions of oxygen or OH minus, and then they will react with an acid to form salt and water as the only product of the reaction. Note, there is an exception to this definition in the reaction of lead-4 oxide with hydrochloric acid. When lead-4 oxide reacts with hydrochloric acid, instead of producing salt and water as the only products of the reaction, it is also going to give chlorine gas. So from this, you will see that lead-4 oxide will not be considered as a base. Have that in mind, that when you are considering lead-4 oxide, it is not a base. Why is it not a base? Because when it reacted with an acid, it did not produce salt and water as the only products of the reaction. It also gave chlorine. So the implication is that this is more like a redox reaction than a neutralization reaction, because in a redox reaction there is usually oxidation and reduction. However, a neutralization reaction is simply a reaction between an acid and a base to produce salt and water as the only products of the reaction. Moving on, we go to the next person who postulated the definition of an acid, and that person is Bronsted-Lowry. Now, Bronsted-Lowry's definition, there are two people actually. You have your Johannes Bronsted, who is a Danish scientist, and Thomas Lowry. These two scientists put their heads together to come up with a better definition. This was simply because they noticed that not all substances, there were substances actually that exhibited acidic properties, but they don't produce hydrogen ion as the only positive ion. So they looked at it and saw that there are even ions that can actually begin to act like acids. And what does that mean? It means that the Arrhenius definition is not an all-encompassing definition. So they had to put their own definition forward. Let's look at what they had to say. A Bronsted-Lowry acid is a proton or hydrogen ion donor. The implication is that once a substance gives a proton or hydrogen ion, it's an acid. While a Bronsted-Lowry base is a proton or hydrogen ion acceptor. Bronsted-Lowry base accepts protons. Bronsted-Lowry acid donates protons. So let's look at some reactions to help us understand this. Take, for instance, let's take this all out. If you have a reaction, let's say between your bicarbonate ion, and then it is combined with, let's say, your chloride ion. Now, in this reaction, if you have the product to be CO3 2 minus plus HCl, notice something. Bicarbonate ion used to have a proton, but after the reaction occurs, it donated or gave out its proton to chlorine. Hence, this bicarbonate ion, because it gave out, look at it, it used to have one here, but over here it doesn't have anything. This bicarbonate ion is what we're going to refer to as your Bronsted-Lowry acid. On the other hand, chlorine ion does not have any hydrogen, but on going over, you will notice that it has one hydrogen. What does it mean? It accepted, and we say that any substance that accepts a proton is a Bronsted-Lowry base. So just have that in mind. If you are collecting something from anybody, you are a what? A Bronsted-Lowry base. On the other hand, if now you they give them, you are a Bronsted-Lowry acid. So just have that in mind, basically, that when you are considering a reaction between two substances and one of them gives a proton, why the other accepts, the one that gives a proton is the acid, why the one that accepts is a base. Now, before we leave this description, every single time a Bronsted-Lowry acid gives out a proton, it tends to form another substance. As you can see here, when HCO3 gave out its proton or hydrogen ion, you notice that we have CO3 2 minus formed. So let's consider this. After a Bronsted-Lowry acid forms a product or donates its proton, it will form what we call a conjugate base. Conjugate because it is produced. That's what conjugate implies. So when you say something is a conjugate, it is conjured. And then it is a base because if you want to reform this acid now, you will need to accept. It would need to accept. So let's consider this again. A Bronsted-Lowry acid will form a conjugate base, which means that a Bronsted-Lowry base would form a conjugate acid. So just have that in mind, that anytime you are considering a reaction between a Bronsted-Lowry acid and a Bronsted-Lowry base, the conjugates are just basically like opposites. You would say a Bronsted-Lowry acid forms the conjugate base, while a Bronsted-Lowry base forms the conjugate acid. But besides that, if you look at this reaction and let's say we reverse it, you will notice that on this side this becomes the acid because HCl would have to give off hydrogen to become Cl minus, while CO3 would have to accept hydrogen to become HCO3 minus. So we are taking this again, that whenever you are dealing with a Bronsted-Lowry acid and a base, a Bronsted-Lowry acid will give conjugate base, while a Bronsted-Lowry base will give conjugate acid. Okay, let's try another example. Imagine we had something like NH4. This is ammonium ion plus your, let's say, HSO4 minus. Some of you might actually start mistaking this thing for ammonia, while some of you will mistake this for sulfuric acid. Please note, this is NH4 plus, Ammonium ion. This is HSO4 minus, not H2SO4. HSO4 minus is a bisulfate ion. So just take note of that. Now, it is supposed to be a weak acid. However, in this reaction, you will notice that it is not an acid at all. It is a base. How do we know? Because after this reaction occurs, you will notice that this is going to become ammonia, while this is going to be H2SO4. So notice, it was ammonium that gave HSO4 one hydrogen and made it to become H2SO4. So the implication is that because ammonium ion was the donor, it becomes the acid, Bronzellari acid. Now, because HSO4 was the acceptor, it becomes the Bronzellari base. So note this, the Bronzellari acid, as we noted, will form the conjugate base, while the Bronzellari base will form the conjugate acid. I hope this was easy to understand because it's quite simple and basic. So with that said, let's go back to our slides. So note this, a Bronzellari acid or base differs from its conjugate by one hydrogen atom. Let's notice that. Now, did you notice that if I consider HCO3 and I'm taking it as an acid, all I need to do to form the base, the conjugate base of this particular guy, if I'm considering it as an acid, is remove one proton. Once I remove one proton, it becomes this. So you notice the difference between this Bronzellari acid and its conjugate base is how many protons? One proton. Now, if I decide to take HCO3 as a base, which means I'm going to add one proton. When I add that one proton, it becomes H2CO3. So notice this. What is the difference between the two of them? Still one proton. So Bronzellari base and its conjugate acid basically has a difference of one proton. So check it out here. Chlorine ion used to have no proton at all, and then the difference is that when it became a conjugate acid, it has one proton. On the case of ammonium, ammonium used to have 4 protons, but then over here, how many does it have? 3. So just have that in mind, that the difference between them is basically the fact that they differ by one hydrogen atom or one proton. Okay, so let's continue. Now, with that said, we would go into the next definition of acids and base, and that is your Lewis acid. Your Lewis acid is more like, I refer to it as like the opposite of your Bronzellari acid. I'll tell you why. Let's look at the board. So I'll tell you why. So it might help you remember the Lewis acid definition. So if we are considering the Bronzellari acid, and on this side we are considering the Lewis acid, let's look at this illustration. First of all, is that the Bronzellari acid is a proton. But on this other side, the Lewis acid is an electron pair. Okay, so we said it is a proton donor, but on this other side, Lewis acid is an electron pair acceptor. So more or less like the opposite, because you know the opposite particle, or the particle with an opposite charge in an atom to a proton, is an electron. And then notice that here is a proton, just one proton, but in the Lewis acid, it's a pair of electrons. So we take it again that you can actually decipher. Once you know Bronzellari acid and you are sure of it, you are definitely sure that you simply do the opposite to get your Lewis acid. So a Bronzellari acid is a proton donor, while a Lewis acid is an electron pair acceptor. Which means if a Bronzellari base is a proton acceptor, a Lewis acid will become an electron pair donor. So it's more like a reverse of the two of them basically. And Lewis noticed that there are some substances that do not even have protons. They do not even accept protons, neither do they donate. However, they have the ability to exhibit acidic properties, hence his definition. So we take it again. A Lewis acid is an electron pair acceptor, while a Lewis base is an electron pair donor. Important thing to note about this Lewis acid and base reaction is that a dative bond is formed between the acid and the base to form a compound or ion. So just note that anytime a Lewis acid reacts with a Lewis base, you would have a dative bond formed. For instance, if we consider a reaction between the ammonia and hydrogen ion, so considering this reaction, we have Now, ammonia has 3 hydrogen atoms. It's supposed to have a pyramidal structure, but I'm not going to use that structure, just to help us understand this particular concept. Then we have hydrogen ion reacting with it. Now, notice that for a substance to act as a Lewis base, it must have at least 1 lone pair. That's something you should take note of. For a substance to act as a Lewis base, it must have at least 1 lone pair of electrons. Okay? Then, for it to act as a Lewis acid, it must need at least 1 lone pair or have an empty outermost shell. These are the 2 conditions. It's either it needs 1 lone pair of electrons or it has an outermost shell that is empty. That is for it to act as a Lewis acid. So after this reaction occurs, basically what happens is that they combine, and then you have that this hydrogen, because it has nothing, would go and attach itself to this pair, and they will now share. Now, in our different study or a different video, you would understand the difference between covalent bonding and dative covalent bonding. In dative covalent bonding, you find out that one of the combining atoms brings the shared pair, and that's basically what happens here. So you notice that hydrogen begins to share of this pair of electrons, and why we are referring to this as a dative bond is because the both of them are sharing it. However, it is only one of the combining substances that brought the shared pair. So basically that, and we have that anytime a Lewis base, as you can see, the Lewis base donated while the Lewis acid accepted, the compound that is formed must have a dative bond. Back to the study. The next thing we're going to discuss is the classification of acids based on strength. Now, there are 2 classes of acids based on their strength. It's either you have a strong acid or you have a weak acid. Strong acids are acids which ionize completely in aqueous solutions, and such acid solutions have a high concentration of hydrogen ion. So the implication is, when you are thinking about a strong acid, the most important thing that should come to your mind is complete ionization. While on the other hand, a weak acid would undergo incomplete ionization. Now, it is not based on the concentration of the hydrogen ions necessarily, but based on the fact that these particular acids would undergo complete ionization. An illustration I like to use is, take for instance, you ask 2 students or 2 people, let's look at the board. You ask 2 people to basically do a work, and what is the work? They're supposed to take the chairs or the seats in their classes and take everything outside. Now, this is the first person with his muscles, and by looking at him, the first thing, he even has 12 packs. The first thing you are thinking is that this is the strong guy. Now, but we will find out that it is highly possible or very possible that this is not the stronger person. And then you have this other guy looking lanky and very slim. So this is boy A and this is boy B. Now, in the class of boy B, there are 5 seats or 5 chairs. In the class of boy A, there are 1,000 chairs. Now, when they were asked to carry out the seats or the chairs in their classes, boy B carried out 5. So, carried out 5. Boy A carried out 999 chairs. And when he went in to carry the last chair, he fainted. Based on our definition, boy A is the weak acid. Why is he the weak acid? Because he did not perform his reaction completely. Boy B becomes a strong acid because when it undergoes ionization, it completed its ionization. The implication is, if you consider a strong acid and you dissolve 1,000 molecules of a strong acid, 1,000 of those molecules will ionize. On the other hand, if you consider something like ethanoic acid is a weak acid, and when you dissolve 1,000 molecules of ethanoic acid, out of these 1,000, only 4 will ionize, which means it has like a 0.4% ionization. So just have that in mind. Now, what is used to identify a strong acid and a weak acid or differentiate between them is that the strong acid undergoes complete ionization, while on the other hand, a weak acid undergoes incomplete ionization. With this said, let's look at the examples. So we have that the examples of strong acids. Strong acids include your perchloric acid, which is your tetraoxychlorate 7 acid. Then you have your sulfuric acid, tetraoxysulfate 6. You have your hydroiodic acid, hydrobromic acid, hydrochloric acid, and trioxynitrate 5 acid. Now, the most important ones you're going to come across is H2SO4, HCl, and HNO3. But these ones are also important that you take note of them. What are your weak acids? Your weak acids are any other acids that are not here. Now, for your curriculum, just assume that you get. For your level of study, assume that any other acid that is not here that you will see in your curriculum is basically weak. So all your organic acids are weak acids. Every organic acid is a weak acid. So just have that in mind, that they will not undergo complete ionization to produce hydrogen ions. Okay, with that said, we would move ahead basically. So weak acids are acids that ionize or dissociate slightly or partially in an aqueous solution. And such acid solutions have a low concentration of hydrogen ions. So examples are your ethanoic acid, your trioxycarbonate 4, your tetraoxyphosphate 5, your trioxysulfate 4, and the rest of them. Basically, these acids are referred to as weak acids. So, what then do we consider when we look at the strength of base? The strength of base, like an acid, is basically dependent on or described or split into two, that is weak or strong. The weak base is a base that ionizes slightly in an aqueous solution to produce positively charged metallic ions in most cases or in some cases, and negatively charged hydroxide ions. A very good example is ammonia. When ammonia dissolves in water, it is going to form the ammonium ion and hydroxyl ion. So your very good example of your weak base is ammonia. Then your strong base include those that dissociate completely, and those that dissociate completely are your sodium and your potassium oxides and hydroxides. So have that in mind, that your strong bases include your oxides and hydroxides of sodium and potassium. Okay, the next classification we are going to talk about is the classification based on composition. So on the basis of composition, acids can either be organic or inorganic. An organic acid is basically an organic compound that possesses acidic property. So anytime you have an organic compound that has or exhibits acidic properties, that is basically an organic acid. Now, the emphasis of this particular type of acid is that they must possess what we refer to as the carboxyl or carboxylic group. The carboxyl or carboxylic group is basically your COOH. So once you notice a compound that has this carboxylic group, automatically it is classified as an organic acid. Examples of these organic acids and their sources. First of all, we have methanoic acid. And methanoic acid is naturally found in ants and bee stings. So when an ant stings or a bee stings you, it actually injects methanoic acid into your body. Then you have ethanoic acid, which is found in vinegar. So when your alcohol is basically completely oxidized, what happens is that it begins or produces vinegar. So just have that in mind, that the acid found in vinegar is ethanoic acid. Then we have tartaric acid. Tartaric acid is the acid that makes your soup sour, and that's why you have the sour taste, and it's also found in grape. Your lactic acid is your milk acid. Your citric acid is found in lime and lemon. Amino acid is produced after protein is digested, and then you have that the ascorbic acid is found in orange. Now, the major organic acids that must be taken note of by every Jamb student includes the methanoic acid and its source, which is the ant and bee sting, the ethanoic acid and its source, which is the vinegar, and then tartaric acid and its source, which is sour soup and grape. Take note of these three. These are the most important ones for your Jamb exam. Then we go to inorganic acids. Inorganic acids are basically acids that are formed from mineral elements. So when they don't have an organic basis, the implication is that it's an inorganic acid. Examples: hydrochloric acid, HCl, elements present hydrogen and chlorine, tetraoxysulfate acid, H2SO4, hydrogen, sulfur, and oxygen, trioxynitrate 5, and the rest of them. Basically, these are referred to as your inorganic acids. The next thing we are going to talk about is the basicity of an acid. Basicity is the number of replaceable hydrogen ions in one molecule of an acid. So when I'm considering an acid, and I want to know its basicity, it is simply the number of hydrogen ions that can be replaced. For your inorganic acids, once you just count the number of hydrogen ions there, that is its basicity. So when I'm considering a variety of acids, for instance, I should have used that. If I have H3PO4 and I am asked what is the basicity for inorganic acid, because it's an inorganic acid, the implication is that the basicity is 3. So once you count the number of hydrogen in an inorganic acid, it describes its basicity. If I have H2SO4, the basicity is 2, so it's dibasic. This is tribasic. If I have HNO3, the basicity is 1, so it's monobasic. So once you count the number of hydrogen ions in inorganic acid, it describes its basicity. However, for organic acids, the basicity of organic acid is dependent on the hydrogen attached to a carboxylic group or carboxyl group. So when I have CH3, COOH, I'm not just going to go and count every hydrogen I see. I'm only going to count the hydrogen attached to the carboxyl group. And how many hydrogen do I have? 1. Hence, ethanoic acid is going to be referred to as monobasic. However, if I have your oxalic acid, which is your C-ethan dioic acid, so if I have this, so notice this, I have 2 carboxylic group, and because I have 2 carboxylic groups, the implication is that I have 2 hydrogen that can be replaced. Hence, the oxalic acid is going to be referred to as dibasic. So as I said, once you are considering an organic acid, you count the number of hydrogens attached to the carboxyl group, and that would give you your basicity. Okay, with that said, we also have acidity basically, which is the opposite of basicity. Acidity is simply the number of hydroxyl ions that can be replaced in a particular base. Just as you have basicity as number of hydrogen ion, you have that acidity is the number of replaceable hydroxyl ions. I hope so far you've been able to understand some little things about the acids and the base. We are going to continue this study in a different section. Thank you very much. Welcome guys to Efiwe, Excellence Without Stress, and I remain your favorite chemistry tutor, Godson. In this section of the study, we are going to be looking into a very important aspect of the study of acids and base, and that is the physical and chemical properties of acids and base. Let's start with the physical properties. Acids have sour taste. So the implication is that when you take your lime and you notice how sour it tastes, that is because it contains an acid. The second property is that acid turns blue litmus paper to red. So also have that in mind. Physical properties generally deal with properties that we can see, touch, taste, basically, or feel. Then we go to the next property, is that acids are corrosive, especially when they are strong acids or concentrated. So the implication is that not just when they are strong, but also when they are concentrated. That's exactly why when you take in a bulk of vitamin C tablets, it begins to cause blisters on the palates of your mouth. That's because vitamin C is ascorbic acid. So when taken in large quantities or in high concentration, when you take a lot at the same time, it begins to give you blisters because it is acidic. Then we go to the next one. In aqueous solutions, acid solutions definitely can serve as electrolytes. Hence, they can conduct electricity. What are the chemical properties of acids? We are going to be looking into 3 major chemical properties. However, there's a 4th one that we'll just consider basically. But the 3 major properties, chemical properties of acids include: number 1, neutralization reaction; number 2, reaction with carbonate salts; and then finally, your reaction with metals above hydrogen in the electrochemical series. So let's get to that. What is neutralization? Neutralization is a process whereby an acid reacts completely with an alkali or base to form salt and water as the only products of the reaction. So you have that when acid plus base gives salt and water, that is what we refer to as neutralization. So as you can see in the reaction, okay, let's put that down. Let's actually write out our reaction on the board. If you consider the acid, as we know, H2SO4 and then it tends to react with your alkali sodium hydroxide to give. Now basically what happens in acid neutralization reaction is, well, I say double decomposition. They just exchange their ions basically. So sodium collects hydrogen's girlfriend, while hydrogen collects sodium's girlfriend. So equal is a win-win for everybody. So we continue. That is going to be Na2SO4, and then water is formed. So basically that it's basic. The reaction is very simple. Okay, if I ask you to do this HCl plus let's say calcium oxide, still the same thing, exchange their anions and let hydrogen take oxygen to form water. So that's going to be calcium chloride plus water basically. So just have that in mind, that is, when you exchange the anions, automatically you just give a salt and water as the only product of the reaction. So basically that's that about neutralization. Neutralization can also be described as the combination of hydrogen ion and hydroxide ion to form a water molecule. So the implication is that if you see a particular definition, instead of describing it with respect to Arrhenius description, this is described with respect to hydrogen ions and hydroxyl ions. So because the most important part of an acid is hydrogen ion, and the most important part of a base is the hydroxide ion it produces. Hence, when we talk about the combination of the hydrogen ion and the hydroxide ion, we are still referring to neutralization. So just take note of that. Neutralization can also be defined as the combination of oxonium ions, that is your hydroxonium ions and hydroxide ions, to form water molecule. In this reaction, salt is also formed. Now what we basically mean is, if you see this is neutralization, because an acid is reacting with a base to form salt and water. On the other hand, the most important part of an acid is the hydrogen ion, and the most important part of a base is the hydroxyl ion, which means that when the two of them combine, it is still neutralization to form water. Now on the other hand, hydrogen ion in most cases will not stay stable, which means that it has to attach itself to a water molecule, forming a coordinate covalent bond, which would now give the product hydroxonium ion. That's H2O+. So the more stable form in which hydrogen ion exists is as a hydroxonium ion. So which means if I now say a reaction between a hydroxonium ion plus hydroxyl ion, it is more or less equivalent to hydrogen ion and hydroxyl ion. So that's going to still give us water. Two molecules though, but it's still neutralization. The point is, if you consider the reaction between an acid and a base to give salt and water, neutralization. A combination between hydrogen ion and hydroxyl ion, neutralization. A combination between the hydroxonium ion, some people call it oxonium ion, it could also be called hydronium ion. The point is, whichever one is still correct. Combining this with hydroxyl ion, you are still going to have water. Let's go back to the properties basically. So we have highlighted the fact that one of the most important chemical properties of an acid is neutralization. We go to the next one, reaction with metals. Now, hydrogen is basically liberated whenever an acid reacts with a metal above hydrogen in the activity series. Before we come to this, let's look at the activity series. Now, the activity series is basically an arrangement of ions on the basis of its reactivity. And as I said, the mnemonics I use for this is King Nana can marry all Zarian female slaves provided he could mercury, silver, gold. So just have that in mind, that this is the mnemonics I use, and you're going to come across it when we come to our study of electrolysis. However, let's just get to understand this. So King is potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen ion, copper, mercury, silver, and gold. So basically, let's move on from that. Now, every metallic ion that is above hydrogen has the ability to displace hydrogen from an acid, simply because it's stronger. You get, it's basic. Stronger person can displace the weaker person, you understand? So if you have a reaction between calcium and something like your HCl, because calcium is above hydrogen in this series, calcium can collect hydrogens. I just say it, one of the ways I say it is that calcium is taking hydrogen's babe from him. So basically, after calcium collects hydrogen's babe, you will notice that hydrogen will be lonely, to be alone. So just have that in mind. That's life for you. If you consider zinc reacting with your sulfuric acid, because zinc is higher, zinc can collect hydrogen's babe, which is SO4 in this case. So zinc will now collect the babe and become the boyfriend, while hydrogen will be alone. The point about it is this: once a metallic ion is above hydrogen, it has the ability to displace hydrogen from the acid and then to give hydrogen gas. If I have copper reacting with hydrochloric acid, the implication is that I'm supposed to have no reaction here. If I have silver reacting with sulfuric acid, what I'm going to have here is no reaction. So just have that in mind. Now, when you are considering your acid reaction with metals, the metals that displace hydrogen from acids to form hydrogen gas are metals that are above hydrogen in the activity series. The next property we are going to be considering is the reaction with carbonate salts. Now, acids react with carbonate salts to liberate carbon 4 oxide gas, salt, and water. The most important gas in this reaction is the carbon 4 oxide gas. So, now, it is also important to note that bicarbonate salts also undergo this reaction. So let's just explain what a carbonate and a bicarbonate is. If you have a salt and it contains CO3 2- as an anion, it is a carbonate salt. If you have a salt and it contains HCO3-, it is a bicarbonate salt. So either of these two, when they react with acids, they are going to liberate carbon 4 oxide gas. Now, mind you, this is also a lab preparation of carbon 4 oxide gas. That whenever an acid reacts with a carbonate salt, it basically gives carbon 4 oxide gas. You should learn that. Now, let's continue. Now, having said this, you would notice that if I react something like your sulfuric acid with your calcium carbonate, automatically I'm going to have a reaction where Ca collects SO4 first of all to form the salt. That's going to be CaSO4. Then you have water and CO2 produced. That's all. That's basically what you need to know. Once it's a carbonate salt, just form the salt, then write water and CO2. That's all. If, for instance, it was HCl, hydrochloric acid, and zinc carbonate, same thing. Zn collects Cl to form this. Then you just put your water and CO2. You can balance out later. If you have, for instance, any other acid, H3PO4, and then it's reacting with maybe aluminium carbonate, and you have CO3 brackets 3, you are going to have aluminium phosphate produced plus water and then CO2. So it's basic. Once a carbonate salt or a bicarbonate salt, okay, let's use for bicarbonate salt. If you are dealing with NaHCO3 and then it is reacting with your HNO3, automatically what is going to happen is Na will collect NO3 and then you have NaNO3. Then you form your water and your CO2. Same thing. So just have that in mind, that anytime a carbonate salt or a bicarbonate salt is reacting with an acid, the products are salt, water, and carbon 4 oxide. And remember, the most important gas in this reaction produced is carbon 4 oxide. Also note that this serves as a lab preparation of carbon 4 oxide. Now, in the case of hydrogen too, a reaction with metals of acids with metals above hydrogen in the activity series would also give hydrogen as its lab preparation. And let's continue. The fourth one, which is not so important, is reaction with sulfite salts to give sulfur 4 oxide gas. So you noticed that when triazocarbonate 4 salts reacted, it gave carbon 4 oxide gas. Also, when triazosulfate 4 salt will react with, because the sulfite salt is a triazosulfate 4 salt. So if triazocarbonate 4 gives carbon 4 oxide, trioxosulfate 4 would also give sulfur 4 oxide. So let's just consider one reaction just to buttress this point. So you have that Na2SO3 reacting with an acid HCl aqueous. If this reaction is to occur, you will notice that you're going to have NaCl, water, and sulfur 4 oxide gas, basically. And that's that about that reaction. So the next part of our study is going to be the physical properties of your alkalis or base. The very first one is that they have bitter taste. And the next one is that they are soapy to touch or feel. So the reason your soap is slippery is because in the production of soap by saponification, an alkalis is basically used. They also turn red litmus paper blue. And then concentrated forms of caustic alkalis such as your sodium hydroxide and your potassium hydroxide are actually corrosive. Now, there are three major reactions that an alkalis or base undergoes. The first reaction is neutralization. every base reacts with an acid to form salt and water. The second important reaction is a reaction with ammonium salt. So note this, that whenever a base reacts with an ammonium salt, an alkalis, more specific, reacts with an ammonium salt, if you heat an alkalis with an ammonium salt, let's say sodium hydroxide, and you heat it with an ammonium salt, ammonium chloride, the gas that is going to be produced is ammonia. So this is going to happen. Sodium would collect Cl, so a salt is going to be formed. You have ammonia formed, and then you have water. So basically, that's how the reaction goes. If you have potassium hydroxide and then it is heated with ammonium sulfate, the implication is that you're going to have the same thing. Potassium will collect SO4, so that's going to be K2SO4. Ammonia will be formed, and then you have water. So basically that a base is heated with an ammonium salt to give off ammonia gas. Note that this particular process is going to serve as the lab preparation of ammonia. The third reaction we're going to be considering is a reaction of your acidic oxides with your alkalis. So anytime you consider an acidic oxide, an oxide of a non-metal that dissolves in water to produce an acid. Examples include carbon 4 oxide, sulfur 4 oxide, nitrogen 4 oxide, sulfur 6 oxide, and the rest of them basically. So when these oxides react with your alkalis, they would produce salt and water. So when carbon 4 oxide reacts with your sodium hydroxide, it's going to give your sodium carbonate and water. Let's continue the study in a different section. Thank you very much. Welcome guys to Efiwe, Excellence Without Stress. And in this section of the study, we are going to be considering the uses and preparation of acids and base. Now, let's consider the preparation of acids. Acids can be prepared using the following method. The first one is dissolving an acid anhydride in water. An acid anhydride is an oxide of a non-metal that dissolves in water to produce corresponding acids. So the implication is that when you dissolve any of these acidic oxides in water, you can also refer to them as acidic oxides, automatically you produce an acid. As you can see, SO2 plus H2O give us H2SO3. CO2 plus H2O give us H2CO3. SO3 plus H2O give us H2SO4. So that's basically what happens with this method. The second method is by combination of the constituent elements. It is important to note that this method is characteristic to your hydrohalic acids, that is acids that are produced from your halogen and hydrogen. So just note, as I said, that whenever you are dealing with your hydrohalic acid like your hydrochloric acid, hydrofluoric acid, bromic acid, hydroiodic acid, these acids are produced by direct combination. So as you can see, burning hydrogen in chlorine in the presence of activated charcoal as the catalyst yields HCl gas. This HCl gas is now dissolved in water to produce the hydrochloric acid. So note, the gas is not the acid because it doesn't have protons as ions in this gaseous or covalent state. But when you now dissolve it in water, it produces its ionic form. Heating a gas plus hydrogen gas and bromine vapor in the presence of platinum as catalyst produces hydrogen bromide, and then when you dissolve it in water, you get your hydrobromic acid. The next and final method of producing an acid is by double decomposition. With respect to this, I am going to need to do a little bit of an illustration. Okay, so when we consider our screen, if you consider your strong acids, basically you have that your strong acids are HClO4, H2SO4, Hi, HBr, your HCl, your HNO3. Okay, so that's that basically. Now, if you consider these strong acids, you will notice that this is in an order of decreasing strength. They are all strong, but definitely one has to be stronger than the other. So basically that. Now, to produce an acid by double decomposition, you simply use a strong acid or a stronger acid and react it with a salt of a weaker acid. Once you react it with a salt of a weaker acid, you are going to get the acid of the weaker salt. So look up. Let's say you have H2SO4 and then you want to produce hydrochloric acid. to produce hydrochloric acid, because H2SO4 is stronger than hydrochloric acid, you can use H2SO4. So H2SO4 plus a salt of hydrochloric acid, which is sodium chloride. And when you do that, a double decomposition occurs. This would be exchanged and H will now collect Cl. So the implication is that you're going to have HCl plus Na2SO4. So note, for this process to occur, a stronger acid has to react with a salt of the weaker acid. And once that happens, automatically the weaker acid is produced. Let's say, for instance, you want to produce your nitrate or nitric acid. What's going to happen is you could use any one of these guys, including HCl, because HCl is stronger than your nitric acid. So if you use a stronger acid than the acid you want to produce, you react it with a salt of that acid you want to produce. So let's say KNO3. Once that happens, you are going to have KCl plus HNO3. So this is basically a reaction where the stronger acid displaces the weaker acid, and then automatically the weaker acid is produced. So having said this, another thing that should be noted is that for this particular process, you either consider strength of acid or volatility. And in the case of considering volatility, the order of arrangement for volatility, basically, I'm saying this because ethanoic acid is one special weak acid. It's not supposed to be amongst the strong acid, but then it has a very low volatility. So considering that, if we look at this, you will notice that we're going to have HClO4. This is not the order of strength, this is order of volatility. HClO4, you have H2SO4, then you have ethanoic acid. Then you now continue downwards, HBr, HCl, and then you have your HNO3. Now, looking at this is in an order of increasing volatility. So which means the ones that are down are more volatile than the ones that are up. Now, these ones that are up, the less volatile plus salt of more volatile will give more volatile acid and salt. So just have that in mind, that based on volatility, you will notice that ethanoic acid can be used to produce hydrochloric acid because it is less volatile than hydrochloric acid. So the implication is that if you write the reaction CH3COOH, this time around we're not considering strength. There are two things you consider, strength and volatility. But when you are dealing with ethanoic acid, what you consider is volatility and not strength. Hence, CH3COOH plus NaCl is going to give a feasible reaction where you have CH3COO Na and then HCl acid is formed. So that's that basically. So note that in this reaction, Na will have to come here while hydrogen has to combine with Cl, and when that happens, this is going to occur. The reason this is occurring is not because ethanoic acid is stronger. It is occurring because when you are dealing with ethanoic acid, you consider volatility instead. With that said, looking at the slide, the implication is this, that whenever you are dealing with your double decomposition, to displace a weak or more volatile acid from its salts, you are supposed to use a stronger or less volatile acid. So I said that if you are dealing with ethanoic acid, please consider volatility and not strength. Okay, having said that, we would be going into the next one, which is the preparation of base. How do we prepare base? Dissolution of reactive metals in water is the first method. So if we consider our activity series one more time, King Nana can marry all Zarian female slaves provided he could mercury, silver, gold. Now you will notice something basically from here. Any metal, the first three metals, which are potassium, sodium and calcium, can actually dissolve in cold water. To give hydroxide and hydrogen gas. So take note of this reaction, that when these ones dissolve in water, they dissolve to give, in the sodium and potassium dissolve explosively, their reactions are more vigorous than that of calcium. So just have that in mind. And then in the case of sodium, you have bubbles formed. Anyway, moving down. So from here down to tin, these ones can only react with steam. That is to say, and they are going to give oxides of metals and hydrogen. So if we are considering a reaction here, it means that if we consider let's say zinc plus H2O2 gas, what it is going to give is ZnO plus hydrogen gas. Basically, if it is iron, we are considering Fe plus H2O2 gas. What we are going to get is Fe3O4 plus H2 gas. Balancing out, this is 3, this is 4, this is 4. So basically, you notice that an oxide of a metal is also a base. How did we get this? By reacting steam with that metal. Once you react a metal, these metals, magnesium, aluminum, zinc, iron, and tin, with steam, basically what they are going to give is the oxide of the metal and hydrogen gas. However, these other metals will have no reaction. So basically, that the metals that can dissolve in cold water include potassium, sodium, and calcium. However, these ones can react with steam to still give oxides of metals, which are also bases. Okay, moving ahead to the next one. We would also consider direct combination of metals with oxygen. So if you are to consider oxygen directly, you would notice that if oxygen combines directly with some metals, like in the case of calcium plus oxygen, you are going to have calcium oxide, which is also a base. If you react sodium plus oxygen, you are going to have sodium oxide, which is also a base. So have that in mind. Now, whenever you are dealing with direct combination of metals, it also leads to the formation of your base. Then finally, insoluble hydroxides are produced by a reaction of an alkalis with corresponding salt. Now, remember that we said that an alkalis is basically a soluble hydroxide. So the implication is that when you react an alkalis, let's say sodium hydroxide, with any other metallic salt, let's say for instance zinc chloride, you are going to produce an insoluble hydroxide because there will be a double decomposition. So Na will collect the Cl, while zinc will collect the hydroxide. So that's going to be NaCl plus ZnCl2. So balancing out, this is supposed to be 2. So that's that basically. So anytime you are dealing with you want to produce an insoluble hydroxide, just bring an alkalis and react it with the salt of the corresponding guy. Okay, let's say you want to produce something like aluminium hydroxide. You have to react sodium hydroxide with an aluminium salt. So Al2 bracket SO4 bracket 3. If you do this, you are going to have Al bracket OH 3 produce plus sodium sulfate. So basically, that is the general concept behind that when you want to produce this, all you need to do is, once you perform your reactions, you are going to have a reaction between an alkalis and a salt of the corresponding hydroxide, insoluble hydroxide you want to produce. If you do that, they will exchange their ions and that insoluble hydroxide is produced. So that is that about the different lab preparations of a base. The next concept we are going to get into is the uses of an acid. Let's consider the uses of some acids. Acids are useful chemicals which are used in many industries to make other consumer chemicals such as fertilizers, detergents, and drugs. One of the most important acids is your tetraoxosulfate 6 acid. It is needed by industries to make chemicals used as drying agent. It is a dehydrating agent. It is used as an electrolyte in lead acid accumulators and is required in the oil refineries. They are used in industrial processes, as we said, as drying agent, oxidizing agents, and catalysts. HCl is needed by industries to make chemicals used to remove rust. It is also used to clean the surfaces of metals for electroplating. Acetic acid or ethanoic acid is used in preservatives in food, so it's used for preserving food. It is used in dyeing silk and other textiles. Citric acid is used in making fruit juice. If you consider your trioxynitrate 5 acid, it is needed by industries for making fertilizers and explosives. Boric acid is used as a mild antiseptic or a germicide. Tartaric acid is used in baking powder, soft drinks, and in health salts. Acetic acid which is also ethanoic acid, is also used, as we mentioned, in preserving food. This should be a repetition of what we wrote earlier. And then finally, fatty acid is used in the manufacture of soap. This is a process known as saponification. Let's now consider the uses of our base. Base, as we know, is used in manufacture of soap, and the process is known as saponification. You also have that sodium salts and plastics produced from the base are used in petrol refinery. With that said, let's consider the uses of alkalis. Sodium hydroxide is used in the manufacture of soap, saponification process, and the salts of sodium produced from this sodium hydroxide are used in the plastic and petrol industries. Potassium hydroxide is used in the manufacture of liquid soap, also saponification, and is also used in the dyeing and electroplating of substances. Calcium hydroxide is used in the manufacture of mortar, cement, plaster of Paris, and also used in dissolving acidic soil. So calcium hydroxide is used to reduce acidity of the soil. Magnesium hydroxide is used in the manufacture of toothpaste and is also used as a laxative. You also have that your aqueous ammonia is used for bleaching clothes and is also used in detergent production. With this, we have come to the end of this section of the video. Thank you very much. Welcome guys to Efiwe, Excellence Without Stress. In this particular section of the study, we are going to be considering salts. Now, a salt is referred to as the compound formed when all or part of the ionizable hydrogen ion in an acid is replaced by a metallic or ammonium ion. The point is, once you replace hydrogen ion in an acid with a positive ion, whether it is complete replacement or partial, what you automatically get is a salt. So if we consider a reaction between H2SO4 and KOH, you will notice that if the products are KHSO4 plus H2O, this is still a salt, even though the hydrogen ion was not completely replaced. So one of the hydrogen ion was replaced by one metallic ion. So what is formed here is a salt. On the other hand, if there happens to be a complete replacement where you have K2SO4, it is still a salt. So basically, when a positive ion replaces, and that positive ion has to be a metallic ion or in most cases an ammonium ion, once that happens, automatically a salt is formed. Okay, so going back to our study, we are now going to be looking into the different types of salt. There are 5 types of salts, namely normal salt, acid salt, basic salt, double salt, and complex salt. With the first one, a normal salt or normal salts are the salts that are formed when all the replaceable hydrogen ions in the acids have been completely replaced by a metal ion or ammonium ion. So the implication is that when you say something is a normal salt, the implication is that you are not going to see any hydrogen ion. Like here, you have a hydrogen ion, so this is definitely not going to be referred to as a normal salt. No, this is not normal. But this one where you have that there is no hydrogen ion, there is no hydroxyl ion, this one is normal. Okay, moving ahead to the next one. The next type of salt we are going to be considering is an acid salt. An acid salt or acid salts are basically formed when the replaceable hydrogen ion in an acid are only partially replaced by a metal. So you will notice that one major characteristic of an acid salt is that the acid salt will have hydrogen ion. Acid salts also turn blue litmus paper red, so it means that they are acidic in nature, and they can be converted to normal salts if the remaining replaceable hydrogen ion is replaced with another metallic ion. So as you can see, KHSO4, when you react with its excess of the base, you are going to have that particular hydrogen would now be further replaced. So examples of your acid, once you think acid salt, just write once you see hydrogen as part of the chemical formula of the salt, the implication is that it is an acid salt. On the other hand, a basic salt is formed when only part of the hydroxide ions of a base is replaced by the negative ion. So it can occur when there is insufficient supply of the acid, and when there is excess of the base. So when this occurs, you will notice that there will be remaining or a remainder of your hydroxyl ion. So once you see OH in a salt, the implication is that it is a basic salt. But once you see hydrogen, it is acidic. Okay, now because of the presence of hydroxide ion in the salt, it has basic properties, which means it can turn red litmus paper blue. A basic salt reacts with excess acid to form a normal salt and water only. So when the remaining hydroxide reacts with the acid, automatically you will get a normal salt. The next type of salt is a double salt. Double salts are salts which ionize to produce 3 different types of ions. So you expect to have 3 ions in a double salt. Good. Usually 2 of these ions are positively charged. So the general formula for a double salt can be given as M plus M3 plus SO4 or M plus M2 plus SO4. I would explain what this actually means. So let's go to our writing screen. So if we take this out, as I said, there are 3 ions, and out of those 3 ions in a double salt, you have to have 2 positive ions. That's why we have a positive ion which is univalent, another positive ion which is trivalent, and then in most cases let's consider SO4 in this case. Now if you happen to have this arrangement as you saw in our screen, you will notice that with this arrangement where you have a trivalent metal, you are going to have that SO4 will just be 2, and then not just that, you would have that the number of water of crystallization in most cases with respect to this salt would be 12. So with that said, if we remove this and then come back to this will be 12 H2O. Okay, so let's consider this. A univalent metal is potassium, trivalent metal is aluminium, and then you have SO4 2.12 H2O. So basically this is a double salt. Why? You have a positive, and then 1 negative, and that is that 3 ions, 2 positives usually and 1 negative. Now on the other hand, if we were considering a particular double salt where you have 1 divalent and 1 monovalent, you are now going to have the chemical formula represented generally as this. In most cases you have 6H2O. Now let's consider this. If for instance I have M2 which is univalent, let's say potassium, univalent, combined with that means I have to have 2 here, you get let's consider a compound that coincides with this. So potassium being univalent, I have 2 of them. Then I think of a divalent metal ion and then put SO4 bracket 2, and once this is done I should have 6H2O. So that's that. Basically this is just a general concept. The general concept is this: 2 metallic ions or 2 positive ions, 2 cations plus 1 anion will collectively give us a double salt. Okay, having said that, we shall move ahead to the next type of salt. Now the next type of salt we are going to consider is the complex salt. A complex salt simply contains complex ions. So once you are thinking of complex ions, you have salts in which a particular central atom is surrounded by ligands. So if you consider something like your copper 2 tetraamine, that's Cu2 plus, surrounded by 4 amines, that's ammonia molecules, this basically forms a complex, and that complex is known as copper 2 tetraamine. So any salt that has a complex basically would form a complex salt. The implication is that if I have this particular complex ion in a compound where you have Cu bracket NH3 bracket 4, all of them attached to SO4, this now is a complex salt. Other examples of your complex include your hexacyanoferrate 3 and hexacyanoferrate 2, that's 6 FeCN. Okay, this is going to be 3 minus for your hexacyanoferrate 3, and then you have Fe hexacyanoferrate 2. This should have 4 minus basically. So these are complex ions. So once you see them in your salts, the implication is that they are complex salts formed. So we could look at examples. As we can see here, you have your zinc 2 tetrahydroxide, which is going to give this particular salt, and then you have your potassium hexacyanoferrate 2, and you have your aluminium complex and the rest of this. So once you have your complex salts, they are going to possess complex ions, and those complex ions will combine with either cations or anions to produce your complex salt. Okay. The next aspect of this study that we're going to get into is the hydrolysis of salt. These reactions basically deal with the action or effect of salts when they are dissolved in water. So note that whenever a salt is dissolved in water, it tends to ionize, and by ionization it means it is going to split into its corresponding ions. Now let's see what happens. If you have a salt of a strong acid and a strong base, the salt formed by neutralization of strong acid and a strong base are neutral in nature as they bond in the salt. So the implication is that when they are dissolved in water, the kind of solutions they will form would also be neutral. Let's consider this for instance. Okay. So if we go back to our screen, take this out, we are going to have strong acids plus strong base. If it gives a salt and that salt dissolves in water, because strong will cancel strong, it means that you are going to have a neutral solution. So understand it like that. Strong acid, strong base, any salt that is formed from a strong acid and a strong base, the strength of the acid will cancel the strength of the base completely, hence the salt is going to be neutral. So an example of such situation: strong acid H2SO4, strong base NaOH. Once this happens, Na will combine with SO4, so that's going to be Na2SO4. When you dissolve this substance in water, it is going to be neutral. So just have that in mind, that if I give you a salt, okay, let me give you a random salt, potassium chloride. Look at this K. This is the base part. The metallic part of a salt is from the base, while the anion part is from the acid. So simply add OH here. Then here that is from the acid, add H. So notice strong base, strong acid, which means strong will cancel strong, and then the salt is going to be what? Neutral. So that's that basically. Now the implication is that if I have a strong acid and then it is reacting with a weak base, what is likely going to be happening? You find out that the salt is going to produce will have strong acid overpowers the base. Because the strong acid is going to overpower the base, this particular salt is going to be acidic. So just have that in mind. Example of a salt of a strong acid, let's put a strong acid HCl and then introduce a weak base, ammonia. So when this happens, the salt that is going to be formed is ammonium chloride. Now look at this salt. If you notice this end, I said the cation part is from the base, so add OH. This is weak base. The only strong bases you have are your potassium hydroxide, sodium hydroxide, and your calcium hydroxide. Those are the ones you should take note of. Then chlorine, HCl, hydrochloric acid, is a strong acid. So when strong acid reacts with weak base, the strength of the acid will overpower the weakness of the base, hence this solution would actually be acidic. But note, that is only when it is dissolved in water. In solid state, it is neither acidic nor alkaline nor anything. It is just a salt. However, putting it in water will tend to ionize it, hence bringing out acidic, basic, or neutral properties. Now let's check out another one. If you have a situation where a strong base combines with a weak acid, what is likely going to happen? The salt it is going to give after hydrolysis, obviously, as we can note, because the base is strong, the salt is going to be alkaline. Yes, it's going to be alkaline. So the concept there is strong base overpowers the weak acid, hence it's going to be alkaline. Very basic. So example is a strong base NaOH is combining with a weak acid, any weak acid, let's say your ethanoic acid COOH. What is going to produce is going to be CH3COONA. Because the base is strong and the acid is weak, strong base implies alkaline solution. And then finally, when you have a weak acid and a weak base, weak means that it's going to be neutral. So have that in mind, that this is the general concept in the understanding of hydrolysis of salt. So let's go back to the slide, just go through them. So you have that if it was a weak salt of weak acid and strong base, the salt form of neutralization would actually be basic in nature. So you have that in mind. And when you say something is basic in nature, it means that the pH is greater than 7. We'll discuss pH in a different section of this study. Salts of strong acids and weak base, the salt formed after neutralization would be acidic. And then finally, salts of weak acids and weak base would form a neutral solution. In some cases, it might be basic. We can't just tell for weak acid and weak base, but generally speaking, it should be neutral since the both of them are weak. With this said, we have come to the end of this study.
Hi guys, welcome to Efiwe, Excellence Without Stress. And in this section of the study, we are going to be talking about pH and pOH. Now, pH is simply what describes the negative logarithm to base 10 of the concentration of hydrogen ion, or you could say it is referred to as the negative logarithm to base 10 of the concentration of your hydroxonium ion, which is your H3O plus ion. So they are basically the same thing. That's the thing. So once you do your negative log of the concentration of the hydrogen ion, you've gotten your answer, and that's that basically. Now, okay, so with that said, the implication is that if I tell you that I have a particular acid and its concentration of hydrogen ion is 0.001, all I need to do is pH would be equals negative log to base 10 of that concentration, and that is 0.001. If I do this, my answer is going to be equals, if we decide to do this, this is going to be minus log of 1 times 10 raised to power minus 3. If I decide to solve this without a calculator, my pH is now going to be equals negative log 10 raised to power minus 3. So according to the log rule, we should bring this down. That will be minus 3 times minus log 10. And if you have this, this is going to be minus 3 times minus log 10 is 1, so minus 1. So this is going to be 3. So just take note of that in solving for pH, you use the concentration of hydrogen ion. What is the next thing that you need to take note about pH? pH scale runs from 0 to 14. And if you have a pH scale running from 0 to 14, from 0 to less than 7 indicates acidity. Then from 7 above, you will have, above 7 to 14, you have alkalinity. Then a pH of 7 is what indicates neutrality. So have that in mind that once the pH is 7, it is neutral. If it is less than 7, it is acidic. If it is more than 7, it is basically alkaline. The next thing you should take note of pH is that you can actually use the pH of a substance to find the concentration of hydroxyl ion. And how do you do that? If pH is equals negative log to base 10 of the concentration of hydrogen ion, and you are asked to find the concentration of hydrogen ion, what you simply do is, first of all, let's remove this minus sign here, and this is now going to be equals, okay, before we get to this. So if we are moving the minus sign, this will now be log of hydrogen ion is going to be equals negative pH. Now, the opposite of log is anti-log, so you have that. The concentration of hydrogen ion will now be equals to the anti-log of negative pH. The other way of expressing this is, since this is log concentration of hydrogen ion equals minus pH, you have that whenever you're asked to find the concentration of hydrogen ion, it would be equals what? Your 10 raised to power minus pH. So take note of this formula, that anytime you're asked to find the concentration of hydrogen ion, it is equals 10 raised to power minus pH. So with this said, if you are now giving the hydroxyl ion, but then we are not giving your hydrogen ion directly, how do you find your concentration of hydrogen ion? Concentration of hydrogen ion multiplied by the concentration of hydroxyl ion is equals 10 raised to power minus 14, which means if you are looking for the concentration of hydrogen ion, it will be given as 10 raised to power minus 14 divided by concentration of hydroxyl ion. And vice versa, in a situation where you are looking for your concentration of hydroxyl ion, it is going to be equals 10 raised to power minus 14 divided by concentration of hydrogen ion. Having said this, the next thing we are going to talk about is pOH. Now, just as pH deals with hydrogen ion, pOH will deal with hydroxyl ion simply, which means pOH is the negative log of the concentration of hydroxyl ion, which means when they are dealing with a base, this is what describes pOH. And having said that, we are going to have that if pOH is equals negative log of concentration of hydroxyl ion, it means that the concentration of hydroxyl ion will now be equals 10 raised to power minus pOH, as we solve using the log rule principle. Or you simply do concentration of hydroxyl ion is equals anti-log of negative pOH. Having said this, the next thing to note about pOH scale is that just as the pH scale, it is ranging from 0 to 14. At 7, if the pOH is 7, it is neutral. Now, it is the opposite. From 0 to less than 17 is alkaline. From above 7 to 14 is going to be acidic. So it's like the opposite of pOH. And then finally, how do I relate pH to pOH? pH plus pOH is equals 14. So therefore, we'll have that 14 minus pH would give me pOH. On the other hand, if I'm now looking for my pH, it will be equals 14 minus POH. With this, we have come to the end of this